Consider the following question. Suppose you have the sequence of primes, Pn, 2, 3, 5, 7, 11, 13, and so on. Is it possible that your phone number, or any string of digits that you choose, show up somewhere in one of these primes? Of course, your phone number or chosen number does not have to be a prime, but we only ask whether this number shows up as a substring somewhere in some prime. For example, the number 55512340001 is actually a prime. So if your phone number is 5551234, then it shows up as the first several digits of this prime number. Now, will this question also depend on the base that we choose to represent this number? More generally, we can formulate the following problem. Suppose you have an increasing sequence of integers called an, and we fix a base b and some word w in base b. That is to say, this w is a finite string of digits using 0, 1 to b minus 1. Can we tell whether w will show up somewhere as a substring in one of these terms in your sequence when represented in base b? Well, let's invent some terminology. Let's say an integer sequence an is encyclopedic in base b. If for any word w in base b, we can find some term an such that in base b, this term contains w as a substring somewhere. So using this, we can reformulate our problem. Are the primes encyclopedic? And does it depend on the base? And are there other sequences that are encyclopedic? And can we come up with some sufficient conditions to tell? Well, the first most obvious sequence that is encyclopedic is an equal to n, all the natural numbers. And this will be encyclopedic in all bases b. Even though this seems like a silly, simple example, we can make the following observation. If the sequence an is not growing too quickly, then it will probably sample through all the possible digit strings in its leading portion. For example, suppose there is an r such that when an, the sequence, goes to an plus 1, only the last r many digit changes, that is, the rightmost digits changes. Then this sequence will be encyclopedic because the leftmost digit will slowly sample through all the possible strings. I kind of think of this as a speedometer on your car, where the last few digits are changing, but if it's changing at a rate only the last two digits, let's say, are changing, then the third one will slowly increment up, and so therefore from the third digit and onwards, it will slowly go through all the digits. So if this is true, then we can write these conditions as the consecutive difference between an plus 1 and an to be less than b to the r. Now, this b to the r is just a constant. So this, we have a first preliminary result. The idea of a subarithmetic sequence. So suppose an is a strictly increasing integer sequence, and let c to be some positive constant. Suppose for all n, we have the consecutive difference in this sequence is bounded by c, then an will be encyclopedic in any base b greater than or equal to 2. So this is the observation that we just made. Again, why is this? Indeed, if for any base you choose b, that is 2 or more, you can always find a power r such that b to the r is bigger than c. So if the sequence an is subarithmetic, then the consecutive difference, which is less than c, will be less than or equal to b to the r. Which means when represented in base b, it will only change the last r digits, which will help it sample through all the rest of the digits through its leading portion. Now let's invent some more terminology. Suppose you have an increasing sequence of integers an, we can always associate a new sequence called its gap sequence, defined by taking the consecutive difference, or sometimes called the forward difference. So Gn, the gap sequence, is defined by an plus 1 minus an. So the subarithmetic proposition says if the gap is uniformly bounded by a constant, then the sequence is in fact encyclopedic in any base b greater than or equal to 2. And some examples, well, of course, any arithmetic sequence is encyclopedic. For example, the sequence of even numbers or odd numbers, or all the sequence of numbers, say 7n plus 2, for instance. These are all increasing integer sequence that are arithmetic, in fact. So the gaps are all uniformly bounded, therefore are encyclopedic in any base. But do the primes have a uniformly bounded prime gap? That is to say, are the primes sub-arithmetic? Well, unfortunately, no. The gap among primes can be actually arbitrarily large. That is to say, if Gn denotes as the prime gap, then the supremum of Gn is infinity. Let's state this again. The prime gap can get arbitrarily large. Okay? So we cannot actually use this proposition. But why are the prime gaps not uniformly bounded? This is not too hard to see. We can see it constructively. We can show that for any integer n, we can find n consecutive integers such that none of them are primes, therefore showing there is a prime gap of size at least n. Indeed, you take any positive integer n and you write down the following n numbers: n plus 1 factorial plus 2, n plus 1 factorial plus 3, n plus 1 factorial plus 4, all the way to n plus 1 factorial plus n plus 1, then notice that the first one is bigger than 2 and divisible by 2. The second one is bigger than 3 and divisible by 3, and so on. So each of them is composite with a proper factor. And so therefore none of these are prime. Therefore there's a prime gap of at least size n. A side remark, of course, the prime gaps are of tremendous interest. And notable open problem is the twin prime conjecture, that is asking, are there infinitely many primes such that the prime gap is equal to 2? That is to say, is the limit inferior of the prime gaps equal to 2? As of currently, 2022, we know that the limit inferior of the prime gaps is some even number between 2 and 246. And this comes from this public project called Polymath 8, by improving Eating-Zhang's method. And this is the current state of this story. But let's get back to the question of where the primes are encyclopedic. We know that the prime sequence is not sub-arithmetic, so we cannot use a previous proposition. But we do know that the growth rate of the primes is not that fast by the prime number theorem. First, let's recall a definition. Suppose you have two sequences, an and bn. Let's write an to the squiggle bn, or we can read it as an is asymptotically bn, if the limit of the ratio is equal to 1. Okay. So the celebrated prime number theorem states, if Pn is the nth prime, then Pn is asymptotically n log n. Now, we won't prove the prime number theorem right now, but you will take it as a folklore, and people should just know it as a folklore. And so we'll take it for granted for now. Now, in the sub-arithmetic case, when an is strictly increasing integer sequence, that is, with a gap that is uniformly bounded by some fixed positive constant c, if we divide by an on both sides, we see that the ratio of an plus 1 and an minus 1 is bounded by some constant over an. And because an is an increasing integer sequence, that ratio is also greater than or equal to 1. So what we get is that the ratio of these consecutive terms is between 1 and 1 plus some constant divided by an. Now notice that an increases strictly. So in the limit, this ratio has a limit of 1 by the squeeze theorem. So if we have a sub-arithmetic sequence, the limit of the consecutive terms, of the ratio of the consecutive terms is equal to 1. And in that situation, we know that it is encyclopedic, that is, when you have sub-arithmetic sequence. So of course, we can ask, is this also sufficient? That is, if you have the ratio of consecutive terms in the sequence with a limit of 1, does that imply AN is encyclopedic in any base B? And the answer is yes. So here's a proposition. If you have a strictly increasing integer sequence AN such that the limit of consecutive terms have of a ratio of 1, then AN is in fact encyclopedic in any base B. In fact, we can make the chosen word to show up in the leading positions of some term AN, which is kind of neat. Let's believe this proposition for a moment. Since by the prime number theorem, we know that Pn is asymptotically to n log n primes, you can show that the consecutive ratios of the primes Pn plus 1 to Pn is asymptotically with a limit of 1. You can show this by using simple L'Hopital's rule. And therefore, by that proposition, the primes are encyclopedic in any base. And therefore, your phone number or chosen string will show up somewhere in some prime. Here are some other examples. If you have a sequence that is given by some polynomial function, Pn, where it is increasing, then we know that the ratio of Pn plus 1 to Pn will have a limit of 1 as n goes to infinity, because this is a rational function with the same degree and the same leading coefficient. And so if a sequence is given by a polynomial function that is increasing, then it will be encyclopedic in any base B as well. So now what it remains is the proof of this proposition, that when we have the limit of the consecutive terms with a ratio of 1, then it will be encyclopedic in any base B. Well, let's try to prove it. So we fix a base B that is bigger than 2, bigger than or equal to 2, and some word W in base B. And let M be the integer represented by W in base B. So M is the actual integer represented by this word W. Now, without laws, W is a word that does not start with a leading 0. If it does, then we can always pad it with some non-zero leading digit. What we want to do is we will show that there is some term, AN, whose leading digits are W in base B. That is equivalent of trying to show that AN is bounded between m times b to the r and m plus 1 times b to the r for some r. Now, as AN is an increasing integer sequence with a limit of ratio of 1, by the definition of limits, we can find some position big N, such that when we are exceeding this index big N, the ratio of AN plus 1 to AN is less than or equal to 1 plus some small number. Here I'll write that as 1 over M, where M is that number of that word. Now, for each k, this quantity M times b to the k is somewhere between two consecutive terms of the sequence. So imagine this sequence AN is increasing. So m times b to the k is trapped between two consecutive terms here. So let that be AN of k and AN of k plus 1. Notice this index n of k increases as k increases. So now, let's take some position r such that n of r is bigger than or equal to n. And so, because the limit of the ratio is equal to 1, this statement turns on that the ratio of AN of r plus 1 to AN of r is less than or equal to n plus 1 over m. This was 1 plus 1 over m. And by rearranging, we can show that A sub n of r plus 1 is less than or equal to n plus 1 times b to the r. So this shows 1/2 of what we wanted. But we've chosen A of n of r plus 1 to be bigger than or equal to m times b to the r. So this is precisely the term that we wanted, that is between m times b to the r and m plus 1 times b to the r. That is to say, the leading digits of AN of r plus 1 in base B is W. has proving this proposition, which is neat. So now some questions. What if the sequence AN do not have a limiting consecutive ratio of 1? Then the sequence need not be encyclopedic in certain bases. For example, if you take the sequence AN that is equal to 10 to the n, then the consecutive ratios is actually 10. And in base 10, the sequence is not encyclopedic at all because it only contains a 1 and a bunch of zeros, right? So you will not be able to find your phone number there. But is it possible that there is another base B such that this sequence 10 to the n is encyclopedic? What about the powers of 2? Is the powers of 2 to the n, encyclopedic over base 10 or over other bases? So these are some questions that we can think about, but our theorem currently to review does not cover. So right now, what we have is this nice proposition that says if the consecutive ratio has a limit of 1, then it will be encyclopedic in all bases. But when the ratio is not equal to 1, in other cases, then we're not sure. And so we'll explore this next time.